Good morning, good afternoon, good evening, whenever it is that you're watching this. This is Evolution Note 6. We are going to be breaking this up into chunks so it's a little easier to manage, just so you know. So let's get started. So we have been talking about what Darwin said about his idea of evolution and how that evolution could have occurred by natural selection. But what evidence do we have that evolution has actually occurred? It's important for us to know the overwhelming mountain of evidence that we have for that. So remember what evolution says, that the kinds of species on Earth has not remained static. It has changed over time. Okay. And remember that Darwin didn't give us this idea. This idea goes back much before Darwin, all the way to Aristotle. So what evidence do we have that life actually has changed? Okay. The answer is lots. And it starts with the fossil record. Okay, so we are going to go through all the different categories of evidence that we have that life has changed over time, and moreover, that change is due to natural selection. But right now, the fossil record. We have ample evidence that life has changed over time because we see it in the rocks. This right here, can you see that? Not sure how close I can get, but this is a rock, but it has obviously got the form that is not just a rock. This is a trilobite. It was once, it and its cousins and so on were once the dominant life form on the planet. Some trilobites were this big, some were smaller than this, but if you look at it, it kind of looks like a roly-poly that you might find in your backyard, but they were crustaceans, which actually roly-polies are. And this fossil is from Morocco, and it's 360 million years old. So this piece of rock, this organism lived 360 million years ago. I'm holding something in my hand that is evidence of a life form from 360 million years ago. So we have piles of fossils just like that. So how do these fossils get made? Okay. Layers and layers of sediment fall every day to the bottom of the ocean. They run off from rivers and they fall to the bottom of the ocean. This process has been going on for millions of years, and that happened in our ancient oceans as well as our modern ones. See if I can show you. This may just look like a rock based on your ability to see it through this camera, but that, if you look at it, if you're able to see it, is a clam. It's a rock, but it is clearly a clam. It's a bivalve. You can see the hinge right here, where the shells would open like that. I've got this. I'm not sure if you can see it, but this is a snail shell. If you can look, you might be able to see the spiral, but it's a rock. Okay. Here, I'm not sure if you can see what this is or not, but this is like a sand dollar. It's a fossil sea biscuit type creature. It's kind of like a sand dollar. Of these little guys, these are all little tiny clam-like, oyster-like things. Now, oh, this is an old, is a piece of coral. Now, obviously the shells I've been showing you are associated with oceans. They're all fossils. These are associated with water, okay? Now, let me tell you where these were all found. These were all found by my friend when she lived in Saudi Arabia a long time ago, back in the 90s, maybe even the 80s. So Saudi Arabia, we know, is a desert. He's clearly, all of these things are definitely associated with living in water. So what does that tell us about Saudi Arabia? Not only do the living things on Earth change, but the whole geography of our planet has changed as well. So there was a time when Saudi Arabia was actually the bottom of an ocean and has been lifted up. And the things were at the bottom of that ocean got buried over time and then lifted up. And you can see something like that in the layers of these rocks that are on the screen. So the dead plants and animals which got buried by sediment millions of years ago got lifted up, and now they're the part of the landmass of Saudi Arabia. So over time, the compression of being buried under the ocean turned those plants, animals, and the sediment all into rock. And that was a permanent record of the plants and animals that lived during that time. Okay, so now, how do we know how old? Let's say we know this trilobite is 360 million years old. How do we know how old that fossil is? Okay, there's a couple of different ways that we can measure the age of a fossil so we know how old it is. There is relative dating, which is kind of like me saying, I'm older than my daughter, but I'm younger than my mother. It's all relative, okay? It doesn't give an exact age. It doesn't say I'm actually 56 years old and my daughter is, but it does tell us how old a rock or a fossil is compared to or relative to other rocks and fossils in nearby layers of the rock. Okay, we'll talk about that more in a minute. Then there's also radiometric dating, where scientists can determine exactly how old a rock or a fossil is by measuring the amounts of radioactive elements present in that rock or fossil. And it can give you an exact age. That rock is 56 million years old, period. Those means are very reliable, and we use them for all kinds of stuff. So now, relative dating, though, our oldest fossils, like this may be not our oldest fossils that we have, but this is pretty old. They are found in the oldest layers of rock. Makes sense, okay? Those oldest layers are near the bottom, which makes sense. If our oldest rock is made out of, sedimentary rock is made out of layers of sediment that were laid down, the ones at the bottom were laid down first, and then other layers were laid down on top more recently. So the oldest rock in a sedimentary rock layer is always near the bottom. The younger fossils and younger rocks are found near the top, like these up here. So older down here, younger near the top. So what do the fossils that we collect actually tell us about life? They tell us that life first appeared on Earth around 3.9 billion years ago. Billion. There are 1,000 millions in 1 billion. This time scale is vast, enormous, and it's hard for us to wrap our heads around sometimes. But life on Earth first appeared around 3.9 billion years ago, and it was very, very simple. It was single-celled. How do we know this? Are there fossils of single cells in rock? And the answer is yes, there are, if you know how to find them and look for them. What you're seeing in this rock, it's a microscope view of a rock, but you are seeing some single-celled fossils preserved in rock. And what we know from looking at them is that these fossils were prokaryotic. They were bacteria. They were the simplest life forms we know of. First life was very, very simple. That makes sense. You don't start with the most complex, you start with simple and build up. So these first cells had no organelles, no nucleus, just like as we have learned about prokaryotic life forms all this year. So the fossils also show us that this simple life that we started with, the organisms gradually got more and more complex. If we go up, up, up in the fossil record to more recent life forms, they gradually get more and more complex over time. The oldest rocks on Earth have only more simple organisms. The younger rocks have increasingly complex and more diverse, more different varieties of organisms. So this is really important for you to understand. The simple to complex trend in the story of life on Earth is clear in the fossil record. It is absolutely clear. From bacteria to eukaryotic cells to the more complex multicellular life that we have with us today. Now, of course, the fossil record is not complete. Not every organism that has ever lived on the planet has gotten fossilized. Most of them get eaten or they just degrade before they can be preserved. It's the rare few, really, even though we have millions and millions of fossils, that actually get preserved. So there's still lots and lots of fossils, and that simple to complex trend is clearly shown, but there are gaps in the fossil record, but we do fill those in all the time as well. So the fossil record also shows us something really interesting, and that is transitional organisms, okay? If birds are descendants of reptiles, which they are, then if that hypothesis is correct, then we would expect to find somewhere in the fossil record a transition form between those two, an organism that had both reptile characteristics and bird characteristics in the fossil record. We would expect to see these kinds of transitions, okay? And we do find exactly that. We find many examples, but the most famous one is Archaeopteryx. This is a really famous fossil of Archaeopteryx, and if you look at it, you can see clearly that there are the imprints of feathers. Here's feathers in its tail all here. It clearly has wings of feathers, just like our modern birds, okay? Yet, it also has reptilian characteristics that you don't see in birds, okay? So a transitional fossil is a fossil that links one major group of organisms to another. And the fossil record is loaded up with these transitional fossils. We find lots of them for different groups of animals. As we were saying, Archaeopteryx has both reptile and bird characteristics. This is an artist's depiction of what Archaeopteryx might have looked like if we had seen it in when it was alive. Different artists have different interpretations. Here's another one. But what you can see are characteristics that we don't find in modern birds. So let's go back and look. What we see here first that might be most obvious from this fossil is this animal has a long vertebral tail, kind of like your cat might have. But birds don't have tails like that. They have tail feathers, but they don't have a long vertebral tail that sticks out past their body. In addition, you can see that there are claws, and those are depicted by the artists here. There's like these little fingers with claws on the wings, and you can see that here as well. They're also, their mouth is full of teeth. Birds don't have teeth anymore. They have these beaks. So lots of changes. So reptilian characteristics in this animal, teeth, a long bony tail, claws on its forelimbs. bird characteristics in this animal. It has wings and it has feathers. And honestly, today, feather is the diagnostic characteristic for a bird. If an animal has feathers, we classify it as a bird. So there you go. There are other transitional fossils. Whales. Whales were once land mammals. This animal is the great-great-great-great-great-great-great-grandpappy of a whale. It looks kind of like some odd dog, but that is the ancestor of the whale. Mammals evolved on land. Whales and dolphins are mammals, and they had to secondarily return back to water. Clearly, there was some environment at the time this animal was alive that it was a benefit for animals that could survive in water to do so. And so these characteristics slowly evolved. So here's our, the fossil record showing the evolution of whales is brilliant. It is clear. If you go, when someday we can all go outside again to the Natural History Museum in DC, they have a beautiful display showing essentially this exact diagram, but it's 3D, and you can walk underneath it. It's amazing. So I believe this right here is what I just showed you a picture of here. Okay. And this animal actually, is related to this. But what I want you to see is that slowly over time, and we have the fossils that show us exactly how this transition happened, this dog-like animal slowly became adapted over many millions of years to live in water. And today our modern whales came from that origin. Okay. So that's where we'll stop with that. We'll pick up with our next bit of evidence in the next podcast. So you guys hang in there. Take care. I love you. I hope you're doing well.